Hello, CS 345, 545 AI students. In class, or on the Zoom recording, you would have seen this following notebook as explicated by Professor Stoiber. And we have gotten questions on some of the exercises for the midweek exercises. So we're going to run through how to do one of them, and that should give you enough so that you have confidence to do the others. So we're starting with the unmodified notebook, and I cleared all the outputs, so we're going to have to do the imports, and then I copied it down into the exercise those parts of the notebook which we are going to need. So exercise number 1 here is going to use charges as the target variable. So let's just read the data frame in. This is just copied. There's no difference from before. We have the 8 attributes of the input data, and before we were targeting insurance claim as the output, and the input, called the features, were all these other things were the input features, and the output was this. Now we're going to do, in this exercise, the output will be charges and the inputs will be the other 7 features. So we've read in the data frame. Splitting it is exactly the same code. You just copy that code, and over here we're going to, as it says, pop out the target variable. And before, this was insurance claim. This was insurance claim before. Okay, now it's charges, and then that'll remove the charges column from here and put it into a new data frame, which was training labels. But labels is what we'd use for categorical variables. So let's just call those training test vals. You can do what you want. You don't have to change it. But these will be the output. So the input features will be everything except the charges, and the output features will be the charges, which are in these cells called test vals. Okay. Looking at our data frame here, we notice all the input features. And insurance claim is there now. Charges was missing. All right, that's what we want. All right, but these are still categorical. So we need to take those categorical features and convert them to what? Convert them to one hot. So here I just copied down the cells which converted everything to one hot, and we'll notice that sex is categorical, and smoker was yes or no, that's categorical, region was categorical, and insurance claim is now a categorical feature among our input features. So I had to add insurance claim here. Insurance claim was not originally, that looked like this. Okay, so we put insurance claim in there as one of the features which needs to be turned into one hot. This will convert it into one hot. So I copied those cells down here. I added insurance claim as a feature which needs to be converted to one hot. And now let's take a look at what that looks like. All is the same except that charges is missing, and then here is the insurance claim feature which has now been added. All right, let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. There's 13 features here. I wish to point out that in the original notebook there were 12 features there. The approved and denied for the insurance claim was not there, so that's 13 minus 2 is 11, and then charges that was there made 12. So if we looked at our original notebook, I've cleared all the outputs, it's not there, but when it showed you, you would have counted 12 of them. And then over here in the model was a little bug, and the little bug is it says that the input had 11 features, but really it had 12. So that should have been 12 originally, like that. Okay, but in any case, now it's 13. We just counted 13 features. Okay, so we've split it. We've pulled out the target, which is the charges. We've encoded all of the input features, and the next thing that was going to happen is that they would normalize all the numerical features. And what we have here now is that our target variable is now a number. We need to normalize that charges to 0 to 1. How can we do that? Well, for a couple of reasons, we're going to do a straight linear normalization. We're just going to divide by the max type of thing. Okay? And that should do it for us. And there's a couple reasons we want to do this. We don't have any reason to believe that charges are somehow rather normally distributed anythings. And we also were instructed to use a linear output layer. So if the output of our neural network is from a straight linear thing, then let's, okay, honor that. So we're just going to linearly scale the charges for a number to be between 0 and 1. So what do we need to do? We need to get the minimum and maximum charges, right? Okay, so Cmin, minimum charge, will be, well, what we're going to do, we notice that before we split it, we read this thing into a data frame called insurance, right? So we read everything into a data frame called insurance, which we then split into training and testing. So if we want the absolute max, let's just get from the original whole data set. Okay. That's the absolute minimum. And the maximum similarly. And now we could print those out. Let's print those out. And we want to normalize it, right? So how can we normalize it? Well, we'll just take the value minus the minimum over max minus min. So okay, and let's just call this the normalization factor. Was what? Okay. Excuse me. So that's the range. The range of charges goes from min to max. So dividing by the normalization factor gets that down to 1, and the multiplying by the normalization factor should restore it, right? Normalization factor. Okay. So let's see what happens here. And then we want to do the same thing for the test valve. So these are the outputs, right? So the output will be the charges normalized to be numbers between 0 and 1. And we'll just print some of these out. Okay, so this says that our minimum charge was about $1,100. Our maximum charge was almost $64,000. Our normalization factor is going to be about 63,000. And now, what did we look at here? So this was our test values, right? So, okay. Anyway, this is the normalized versions of those values. Okay. So, for the features, we can do the same normalization we did before. All right. So here I think we picked the training features to train a normalizer on. Now this normalizer is rather different. This normalizer is computing mean, standard deviation, and the normalized value is going to be standard deviations above or below the mean. Okay, which is okay for a lot of data, but it didn't make any sense for charges which are being linearly, predicted and things like that. Okay, so this thing did not change. This was the same as the before. Now we're going to define our model. So it's going to be sequential, one layer after the other. It has a normalizer. The input shape actually now has 13 features. Before it had 12. 11 was a bug because we subtracted one input feature, which was charges, and we added two input features, which was accepted and denied. All right, so this is now going to be 13. Okay. And the output, we have only one thing we're predicting. Before it was binary two possibilities, yes or no, thumbs up and thumbs down. So we used two output neurons, one for the thumbs up case, one for the thumbs down case, accepted and denied. But now we just have one number coming out. So there's one output neuron. And the activation will just be linear. And if we don't say linear, if we just leave activation off, that's the default. So that will be our model. Notice what we've changed. We've changed, the input shape, and we've changed the output shape. Okay, now we want to compile it. And what about our loss function? Binary cross entropy is used for categorical data, right? So let's just try mean squared error, which is a good thing to use for numerical data. And now for metrics, accuracy makes no sense. That's percent correct. So we've got, it's not counting how many correct items we have here for the charges prediction, because the charges prediction is going to be real valued numbers. What we really want to do is find out how close are we on average. So MAE is mean absolute error. So we're going to take the absolute values of the errors and average them up. So this is on the average, how far off are we? Okay, so if we're up by a little bit or down by a little bit, that counts as the same quantity of error. The mean squared error, of course, is very similar, but it's looking at the square of the error terms in order to emphasize the things that are a little bit different. Okay, and now, did I compile this? No, let's compile it. And now finally we need to fit. Remember, this is now training vals, not features anymore. Okay, and nothing else needs to change. we can just let her rip. But this is training values, training features. Okay. And it runs for a bunch of epochs. And what do we notice? Well, we notice that the absolute error here goes from 0 to 1. So it's essentially it's what percentage of that normalization factor are we off by? Because if this was 1, it would be $62,000 off. If it was 0.1, it would be $6,000 off, right? So this is saying that we're getting within 7% of the correct charges. All right, that's what this mean absolute error means. Okay, so let's just try this on the test values, test features. And now it's, we had a little bit of overtraining there, didn't we? We're up to about 8%, okay? And if we want to, all right, we could then just see how big that is, okay? We could get the MAE out of the model, but let's just put in another, manually put in another thing, and we'll just say 0.780 times the normalization constant, right? Normalization factor. And that'll tell us how many dollars we are on the average off. So the charges went from about 1,000 to 65,000, 64,000, and our average prediction on the test data is about $4,900, within $4,900 on the average. We could try to train it some more. If we just do this again, we'll train it some more. Okay, and you'll notice we're not getting any better here. All right, seems to get a little worse at some point. And now we have just a little bit worse here. Okay, and if we wanted to play with it a little bit, we could go back and change the learning rate. Then that's going to be changing the learning rate is going to be something that's in another one of the exercises. So anyway, I thought that by going through one example, it would show you, of the things that are in this notebook, which ones you need to go in. What are the places in the notebook that you need to go and modify in order to adapt to the exercise, all right, in terms of preparing the data and creating the TensorFlow neural network model. Its architecture changes so much because it's slightly different data in terms of normalizing that we needed to do, and then testing it and evaluating the output to see what it looks like. So you have several other exercises that are due also, and the main idea is the same. Some of them will have categorical outputs, and another one you'll be playing with the learning rate, which I just suggested you might want to change. Anyway, I hope this was helpful. Thank you.